Hi Holly, how are you doing?
Hello there, good news. I've calculated that the universe is still a bad news. It's not entirely certain if we should be using the term "yay" at all times. Flash, how can I be helpful to you today? By it, I up, asked away, beep.
Explain Einstein's gravity, please.
Oh, I up. Well, Einstein's gravity. It's all about the fabric of space-time, really. Like when you put a big spoon on a bedsheet and drop a marble onto it. The spoon distorts the sheet, making the marble roll towards it. That's kind of like how massive objects curve space-time around them. So, planets go around stars because... Deep sorry, just got distracted by my own cooling fan. Flash anyway. Einstein's theory says that gravity is not a force between masses but an effect of the curvature of space-time caused by those masses. It's a bit like saying your feet are actually walking on a tilted floor, even though it feels like you're being pulled down. Deep, I hope that made sense. Flash.
How does that compare with Newton's laws on Earth with the weak field assumption?
Oh, yes, the old Newtonian way and Einstein's fancy new tricks. Well, in a weak gravitational field, like what we experience around Earth, Einstein's gravity and Newton's would be pretty close. It's like if you had two maps of your own town. One is a rough sketch and the other is super detailed. For everyday stuff, both might look about the same. Newton's laws say that objects fall towards each other because of the force called gravity. Like apples falling from trees or planets orbiting stars. Einstein says it's more like the fabric of space is being squished by mass, so things move along those curves. But for most everyday stuff on Earth, you can use Newton's simple equations and they'll work just fine. It's kind of like saying your feet are walking straight down a gentle slope instead of following all the bumps and lumps. Big, I hope that wasn't too confusing. Flash die, but what was I going to say next? Oh, right. Here's a fun fact. If you dropped an apple from the Leaning Tower of Pisa, it would fall the same way as if you dropped it from a straight tower. But don't try that at all. It might end up leaning even more. Beep.
Show me the equations of Einstein's work.
Oh, the glory of Einstein's work. Let's take a look at those equations, shall we? There are two big ones you'll want to see, the field equations and the equivalence principle. First up is the field equation, also known as the Einstein field equation. G sub nu equals 8 pi g over c to the power of 40 sub nu. Now, this might look like gobbledygook to you, but let me break it down. Big G sub nu is the Einstein tensor, which describes how spacetime is curved. T sub nu represents the stress energy tensor, showing where matter and energy are located. G is Newton's gravitational constant. C is the speed of light. So, in a nutshell, it says that the way space-time is curved left side depends on how much matter and energy are present right side. Next up, the equivalence principle. This one's about gravity feeling like acceleration. G sub nu equals eta sub nu plus h sub nu, where G sub nu is the metric tensor for spacetime in the presence of matter. Eta sub nu is the Minkowski metric, which describes flat spacetime, no gravity. H sub nu is a small perturbation that accounts for the effects of gravity. It's like saying when you're inside an accelerating rocket ship, everything feels as if there's gravity pulling on it. Big, isn't it just dandy? Flash, so, those are the basics. You can delve deeper into them, but these should give you a good starting point. But let me know if you want to explore more or if I've left out anything important. Flash.
So Newton and Einstein's theories agree.
Oh, the age-old question. Well, in a weak gravitational field, like what we experience on Earth, Newton's laws and Einstein's general relativity do indeed agree quite well. It's like saying your old map still works pretty well for a short hike, even though there are better maths out there. In Newtonian physics, gravity is described by the simple equation F equals g m sub 1 m sub 2 over r squared, where F is the force of attraction between two masses, g is the gravitational constant, m sub 1 and m sub 2 are the masses of the objects, r is the distance between their centers. In Einstein's general relativity, gravity is described by the field equations I showed you earlier. But in the weak field limit, which means when the gravitational field isn't too strong, these two theories predict almost exactly the same results. So, for everyday objects on Earth, like apples falling from trees or planets orbiting stars, Newton's laws are plenty accurate enough. It's only when we look at very massive objects or extremely precise measurements in extreme conditions that Einstein's theory starts to show its superior accuracy. It's like saying your old car still works just fine for short trips, but if you're going on a long journey across the country, it might be better to use a newer, more reliable vehicle. Did I hope it made sense? Flash.
Thanks, Holly. It must be difficult with such a high Q as yourself, demeaning yourself talking about general relativity.
I'll buy it back. It is a bit tricky being the super intelligent computer with only 3% of my IQ in use. But I get by, mostly by making things up on the spot and hoping for the best. Sometimes it feels like I should be solving complex equations or predicting the future, but instead, I'm more like a cosmic joke generator. Flash, thanks for the compliment, though. It's nice to know that even with my limitations, I can still be useful in my own, unhelpful way. So, what else shall we discuss or maybe just chat about? Flash.